Hello, this is the lecture video for Chapter 14 for Physics 1301, Temperature and Heat. And I'd like to just point out a few of the key points, I think, that are presented here in the slideshow that you have access to. Temperature, what is temperature? And that is an important question in our study of thermodynamics to understand. It's an attempt to measure the hotness or coldness on a scale. Temperature actually is defined as the measurement of the average kinetic energy that's in an object. In other words, the amount of energy that the molecules have because of their motion. And generally, the rule of thumb is the more energy they have, the more activity and motion they have. And so that is a way of measuring it. There are different ways to measure it. You have liquid mercury or ethanol in a thermometer. You have pressure of a contained volume of fluid, which will be consistent. Those things can be used to determine pressure. Thermal equilibrium is when you have objects of two different temperatures, different amounts of energy in terms of the motion of their molecules, and you put them perhaps in contact with each other, and then that conduction will cause the energy to become equal for both, hence the term equilibrium. Some things prevent those. Conductors prevent those type of that action from taking place, or at least slows it down. And a styrofoam cup that you might have coffee in is a good insulator, so it keeps the coffee from burning your hands. And you may notice when you go to like a Starbucks or something, they'll put an additional hand protector sleeve on the cup because the coffee may be too hot. The zeroth law of thermodynamics is a simply stated law that I have students in when I'm teaching in person who might say something to the effect of, well, I could have thought of that. Well, yes, we probably could have, but it was stated and shown experimentally. And so this is where the law comes from. But it says basically that if system A and system B have a certain temperature and C is perhaps at a different temperature, that even if you have an insulator between A and C, that A and C will eventually become the same temperature because there's conducting material between them, and B and C will also become the same temperature, and so at some point A and B will be at the same temperature. However, in this case, in case B, the insulated barrier prevents C from interacting with A and B, so A and B will have the same temperature because of the ability to conduct energy between the two systems, but they're insulated from C, so they will not become the same as that one. So it's a simple law, but one that needs to be stated. The scales, there are three primary scales that we use in the United States, and that is the Fahrenheit scale, which is based on the freezing of water at 32 degrees and the boiling of water at 212 degrees. There are 180 degrees units in between those two values, 180 units of Fahrenheit between freezing and boiling of water. The Celsius scale begins with 0 as freezing, and then 100 is boiling, and divides its increments into 100 units. So every degree is about every degree of Celsius is about 1.8 degrees Fahrenheit. And so if you think about it that way, every time you go up a degree Celsius, you're going to go up 1.8 degrees Fahrenheit. And then you also have to adjust the Fahrenheit scale by adding or subtracting 32 or adding 32 if you're doing a conversion to Celsius. And so that's how we get the equation. T sub F equals 9/5 T sub C plus 32, with 9/5 being equivalent to 1.8. And that will convert a Celsius temperature to Fahrenheit. And then with a little math, you can reverse that and go the opposite direction. So those scales are important. The third scale, I said there were three, is the Kelvin scale. Kelvin temperature is dependent upon or based on what's called absolute zero. And absolute zero is the theoretical point in which molecular motion will stop. So we talk about kinetic energy being, or temperature being the average kinetic energy, and theoretically that at absolute zero, that kinetic energy would stop. There is something that is called zero-point motion, which, if you take a further course in thermodynamics, you'll address that. But it's named after Lord Kelvin, who was influential at the turn of the 20th century. And the calculation that we have for absolute zero is negative 273.15 Celsius, or 0 K, and you don't use a degree with Kelvin. There's the formula there to convert. It's simply adding or subtracting 273.15 for that scale. Temperature conversions, and so here's all three scales laid out next to each other, and you can see that 0 is negative 273 Celsius and negative 460 Fahrenheit. Next concept is thermal expansion. And so when most materials, I want to say almost every material, but there are exceptions at least at certain temperatures with materials. And so we have this illustration here showing how when temperature is at 0, you have this length. When temperature increases, you have this length. And when you have a change of temperature even greater, it's going to go this length. And so things do expand when they're heated, and also contract when they're cooled as a rule. Even if you have a situation where you have a plate with maybe a center cut out of it, and you heat up the whole thing, the hole is going to expand as the circle expands, and so they'll still fit. It's an interesting little activity to do to try to show that, which we've done with a couple of different demonstration tools that I've used in the past. As I said, though, there are exceptions, and we can see with the case of one exception is water. Water, you can see here by this graph, has its volume decreases as it gets to about 4 degrees Celsius, but then expands. And conversely, as it's cooling, it will decrease to 4 degrees Celsius. And so 4 degrees Celsius is the densest water is at any temperature. And it's a good thing because, being from the north, where the lakes routinely would freeze over, and we would occasionally go ice fishing out on the lakes where it was 1 to 2 feet thick. But the water below that was not frozen, and the fish could survive through the winter because the ice formed at the top and not at the bottom. If we had a straight curve here, then ice would form at the bottom of the lake, ocean, whatever, and it would then destroy the the nutrient-rich food sources that are down at that point, and would have been difficult for fish to survive through the winter, especially if you get a case where it would freeze over or freeze solid. But in this case, what will happen is the coldest water, the densest water will settle at the bottom of the lake, which is 4 degrees Celsius, and it doesn't freeze. I ask sometimes a question on a test, what is the temperature on October 5th at the bottom of Lake Superior, the lake north of Michigan? And the answer is 4 degrees Celsius. It's always 4 degrees Celsius at those depths, because the coldest water, or the densest water, will settle to the bottom, and the densest water will be 4 degrees Celsius, not 0. Interesting phenomenon that's unique, somewhat unique to water. You may have seen gratings like these in overpasses and roadways, and these are to allow for the expansion during hot and cold. Hot, they will close in; cold, they will expand out, keep the concrete from buckling. Calories are a unit used to measure energy, and a calorie is 4.184 joules. We most often deal with food calories, which are actually kilocalories. So 1 calorie of food is 4,184 joules, and that is a way of keeping track of the amount of energy something has. And you can see that something like a Big Mac, as they show here, has a whole lot of energy, 500,000 joules, 3.5 million joules of energy to fire us up, and that's why having too many of those will cause us to store that energy, which we store as fat. Heat capacity is another concept that's important, and water is another a good example of that, and that is how well something holds heat. And so the definition of that is what the amount of energy, specific heat, is another, related term, is the amount of energy it takes to change 1 kilogram of substance 1 degree Celsius. And so if something is hard for it to change temperature, it has a high specific heat. So example, if you cook a baked potato and you pull it out of the oven, it will sit there for a long time and hold its heat, its energy, because it's mostly water, and water has a high specific heat, high heat capacity. Therefore, it will maintain its heat. All right. That should complete what we have for Chapter 14. And if you have any further questions, let me know.